Assalamu alaikum. Welcome to welcome to lecture 25 of data mining. So today we are going to start a new topic that is time series data mining or temporal data mining. And this section would be covered from another textbook. This textbook is by Agarwal called Data Mining, the textbook. I think this is chapter 14. The PDF of this textbook, I think, is available online, but I'll also share the chapter of this chapter as well with you. Mhm. Uh, we'll be discussing time series data mining, and most of this discussion would focus on the time series data and its shaping and modeling for various tasks. So we'll be talking about the data itself, and then pre-processing for time series. We'll talk about forecasting or regression for time series. We then talk about classification and clustering. So the key techniques would be quite similar to those that we have already studied before. Of course, because since the data is changed, you will have to do a bit of reshaping and uh, processing appropriate for time series. So that would be the focus for the next 2-3 lectures. So as I said, this is chapter 14 of data mining, the textbook, which is another textbook on data mining by Agarwal. So this is a chapter of the textbook. So I will share this chapter as well with you on LMS. So first, let's start with what exactly is a time series. What is this particular type of data? So this particular type of data is sometimes also contextual data type. And it's a specific type of contextual data type. So in general, for all contextual data types, you have what is known as behavioral, and then you have also what is the contextual attributes. So in the case of time series, the contextual attributes capture the notion of time or order in the data, while the behavior attributes are the actual attributes of interest in most applications. So you can think of, so for example, if you're measuring temperatures daily at a particular location, so temperature would be a behavioral attribute, while the time at which that temperature is recorded is the contextual attribute. Hmm. So in this particular case, the behavioral attribute is continuous. So behavioral attribute can also be discrete. So for example, so attribute in this case, temperature is continuous. Behavior attribute could be discrete as well. For example, maybe let's say it is the name of the web page that a person has visited. So for example, page A, so the contextual attribute would be web page. And then of course, the contextual, sorry, that's the behavioral attribute. B, So web page, and then the contextual attribute would be actually the order in which that web page has been visited. For example, you will have something like this, let's say web page A, B, C, A, B. So this sequence of values, behavioral values, is ordered. So in this case, the behavioral attribute is discrete, and uh, for discrete temporal data, we also call it as sequences. So this is actually a sequence. So for continuous attributes, we usually refer it as time series. So time series, sequence, and sequence would be when you have discrete attributes. So you will find uh, time series and temporal data in general arising from many applications. So sensor data is often time series because sensor will record some information and also record the time or the context at which that particular information was recorded. So context in general could also be other things, like, for example, in GIS application, the context could also be the latitude, longitude, and time at which a particular information is recorded. So here, of course, we are focusing only on time series, so the context is just the time. So medical data is also often time series in nature. Financial data is also time series in nature. The transactions that you make also have time associated with them. So, and then of course, you have, so most of this financial data is usually time series, the continuous attributes, behavioral attributes are continuous. But in other scenarios, you might have behavioral attributes that are discrete, for example, web log data. In this case, in many cases here, the behavioral attribute is discrete in nature. And of course, you can find applications and other domains as well. So in general, time, and I would even say location, space, is almost always a piece of information. Sometimes we choose to ignore it, but in almost everything, we'll have a time associated with it. So even if you have, let's say, a traditional database, let's say recording students at a university like LUMS, you will always, even if you don't explicitly record time, but time is always an important attribute. Let's say if you have recorded the name of a person, let's say Asif, it is possible that the name of the person today is Asif, maybe tomorrow you might change the name. So you'll always need to associate a time with that information. Similarly, if you talk about, let's say, age is by nature time dependent. So age would change today, tomorrow, and so on. So you'll have a time associated with it. Similarly, space is always associated with almost everything. So if you're measuring, for example, atmospheric pressure, so atmospheric pressure would be recorded at a particular time, of course, but you'll also have a notion of space where it was recorded. So all of this other information, which is contextual, is associated with the behavioral information. So sometimes in some applications, we ignore the contextual information, but it is always there. We ignore it for analysis, or it's not useful for analysis. But in other cases, we do consider that contextual information explicitly, like in the case of time series analysis. So coming back to time series data, and assuming that your attribute is behavioral attributes are continuous or numeric. So you can think of the time series as values x, I, that is recorded at some time t, I. So xi is a behavioral attribute. This might be scalar, it can be scalar, or it could even be a vector, or it could be some other data type. It could even be a graph or a table or something else. Of course, for computational purposes, we'll be representing this information in a formal way, and the two most common ways of representation is the scalar and the vector. Okay, so if it is a vector, then if it is scalar, then this is basically a univariate time series. Of course, we will talk about univariate and multivariate later on as well. There is you can think of this in different ways. So if X is a vector, then of course this will be multivariate time series. So what does this mean? For example, it means essentially if you want to relate it to our traditional representation, so we have time as columns, so T1, T2, T3. So these are the dimensions, or you can say the features or the attributes. And for each of these attributes, you have a value recorded. So you have x1 recorded here, you have x2 recorded here, you have x3 recorded here. Okay. So if you view the data in this way, then this is multi-dimensional data with each dimension being a particular time. So the time stems Ti may be uniform or non-uniform. So the time stems may be uniformly spaced or not. So so in other words, the interval between T1 and T2 should be the same as T2 and T3. So that would be uniformly spaced. But if they are not, then of course T1 is telling you the exact time at which X1 is recorded, and T2 is telling you the exact time as X2 is recorded, and T3 is telling you the exact time and X3 is recorded. In many applications, it is somewhat desirable to have uniformly spaced stamps. So if that is the case, then oftentimes, and also when we don't really need to know the exact time, we will just think of this as an order. So you can see the first time step, second time step, 3, 4, and then you have the values x1 here, x2 here, x3 here, and x4 here, and so on. So we don't know the exact time at which a particular value is recorded, but we just represent them by indices, and those indices show the order 1, 2, 3, 4. Okay. So in this case, this would be ordered data, and if no other information is known, then we don't really know whether this order is of uniform or non-uniform. Okay. All right. So that essentially is the introduction to what a time series data type is. Sometimes this is also called temporal data type, interchangeably, but sometimes slight differences are made between the two. Usually temporal would be referred to sequences, but sometimes they are not, so it's kind of used interchangeably. So time series data types are contextual data types. They have contextual attributes and behavioral attributes. Contextual attributes capture the context at which a particular behavioral attribute value is recorded. And the contextual attribute for time series, of course, time. And they could be evenly spaced, or they could be non-uniformly spaced. And we have applications coming from almost all domains. So in our modern world of sensor and IoT, Internet of Things, you always have information recorded and with the appropriate contextual stamp, timestamp, location stamp, and so on. So that makes it a contextual data type. All right. So So we will be now looking at the various steps, processes that can be performed. So we'll talk about, for example, preprocessing. Preprocessing, we then move on to, and within preprocessing, there are various things, for example, missing values and smoothing and so on, similarity. And then we will talk about forecasting, which is one of the most popular applications for time series data, continuous time series data, which basically is about regression. And then after that, we'll talk about classification and clustering of time series. We can also discuss outlier, and also we might discuss motifs detection from time series. This is more applicable to, of course, sequences. So these are some of the things that we'll talk about briefly in this section of the course. Most of this stuff would be kind of extensions of the stuff that we have already studied before. So we will be moving relatively quickly. Okay, so let's start with preprocessing. So whenever you have a time series data, uh, you may come across some issues. So you might have missing values, for example. You might have the issue of noise, for example. Noise, we have already discussed all of these things before. So missing values may be due to some error at a particular sensor, so that value is not available. And noise also might arise due to some transmission errors. So some values that are not from the data generating process, so that would be noise. And also sometimes sometimes the time intervals at which values are recorded are not uniform, but for some applications, we would like to have values at uniform timestamp. So both missing data and values at specific time stamps can be solved using the simple problem of interpolation. So you can interpolate between the existing values and find a missing value, or find a value that was not given or recorded at a particular timestamp. So maybe let's say you have temperature recorded 25, let's say, and then 26 and 35 and so on. Uh, Maybe the first one was recorded at 13 hours, the second was at 14, and usually we would have it to have at every hour, but the third was recorded at 16, so there was no recording at 15. So you can think of that as a missing value, or you can think of it as a problem where the recorded values are not evenly spaced. So you can then interpolate that value. Okay? So we would like to interpolate the value at 15. Okay? So this would be the problem of interpolation. Usually we use linear interpolation. Of course, you can use more sophisticated as well, but they are not usually very accurate or reliable. So linear interpolation is typically used. So essentially, uh, so you can, so in this particular case, so we are talking about 26 and 35, right? So you assume that, and the times are 14, there's 2 hours gap between them. So 14 and 16. So 15 would be exactly between 26 and 35. So simple linear interpolation would simply be the middle value in this straight line that connects 26 and 35. So which would be simply, so 35 minus 26 divided by 2. Why 4? Oh, okay. So you have to add the 26 as well. So basically it will be 26 plus 4.5. So this would be the value at that time which is missing, which is 15. So linear interpolation can be used to find missing values or to ensure that your data set has values at regular time steps. So you can use sophisticated techniques as well, but they're only recommended if you know that the model is based on a sophisticated technique, like let's say exponential model or a square, in any exponential model. So, but in practice, we will stick with the simpler model, which is linear interpolation. So that is missing values and interpolation. So what about noise? So we had studied various techniques for uh, filtering or smoothing out noise earlier on as well. So those can be applied in this case as well. So for example, you can do binning. Now the binning is done in uh, space, meaning that so you bin data uh, over time and then take the average and replace it with the average for that bin. So for example, again, let's say if you have temperature 25, so 26, 25, 27, 26, 25. So you can take bins that consist of 3 values in a sequence. So you'll take the average of this and replace these 3 values with the average. So this will be the smooth value. Of course, there will be boundary effects because simple binning takes fixed bins and there is a change after each bin. So the first bin average would be, so there are 225, 126. So this will be 25.33 most likely. So 25.33, which is, so you can actually do this. So 25 plus 26 plus 25 divided by 3. So you will replace all values with 25.33, 25.33, 25.33, and so on. So this can be used, but for time series, there are 2 other approaches that are more appropriate. So those are the moving average, and the other is exponential smoothing. So the moving average, as the name suggests, has a sliding window as uh, the window over which averages are taken. By the way, you can take averages, which is the mean, or you can also use the median, which will be more robust to outliers or noise, to replace the values in each bin. So moving average basically uses uses sliding windows. Windows. What's happening? All right. So, so for example, if you have the same data that's before 25, 26, 25. So if you take a sliding window of size 3, you will start with the first 3 values, and actually it can be done in both ways. Okay, if you start with the first 3 values and take the average, will be of course 25.33 as before. Then you move the window 1 forward, and then you get the next value. But that next value would be for, so let me just write it here. So you have 25, So if you take the average of all these three, you get 25.33. So would you replace all of these values with 25.33? No, you replace the last value, this one, with 25.33, and then you continue with the moving average stuff. So which is, let's say your next value is actually इसमें पीछे वाली value change होती है. So let me just, not this one. Let me write it again. So 25, 26 and 25. So मूविंग एवरेज आप कर रहे हैं तो इसका एवरेज जो बना है वो आपके पास आया है 25.3. तो यू रिप्लेस द फर्स्ट वैल्यू 0.33 एंड देन यू मूव द विंडो फॉरवर्ड. उसके बाद क्या था, 26 था, 25 था और 27 था. अब इन तीन का आपके पास एवरेज लेंगे, वो नेक्स्ट वैल्यू बन जाएगा एंड देन यू मूव द विंडो फॉरवर्ड. ऑफ कोर्स एज यू कैन सी, जब आपके विंडो लास्ट पे आएगी वहां आपके पास कुछ सेल्स रह जाएंगे जहां एवरेजिंग नहीं हो सकेगी. So this is the boundary effect of the moving average problem, moving average technique. So पहली वाली values हो जाएंगी smoothed out, but आखिरी वाली नहीं होंगी, because the window of course cannot go after the values have ended. So in this case, let's say if I do that, so 25.33, the अगली तीन की average जो है वो 26 है, ठीक है. तो then you of course you have 26, 27 or let's say 25. इन तीन का फिर निकलेगा, which is the third value and so on. So you continue in this fashion. So this is the moving average. Of course, it has the issue of boundary, especially at the end. The third technique is exponential smoothing. So this is actually also a form of moving average, but the moving average is defined by a parameter. And from a theoretical perspective, the window is exponential in nature. Of course, we won't go into the theory too much. We'll just explain the idea quickly. So actually the technique itself in terms of idea is very simple. So you want to get the estimate at the ith position, xi. So this is given by the alpha, which is a parameter which ranges between 0 and 1, a scalar, multiplied by x I. This is the actual value actually, xi, and the xi on the left hand side is smooth value. So plus 1 minus alpha into xi minus 1. Okay. So this is essentially the simplest form of exponential smoothing. Alpha, as I said, is a scalar that lies between 0 and 1, and that controls the degree of smoothing. So for example, if alpha is 0, so what does this mean? If alpha is 0, we have returning the previous value as the next value. And if alpha remains is 0 for your series, then essentially you will get x0 as all the outputs. So there is actually no smoothing going on, just returning the starting value for all the points. So straight line आप समझ लें आ रही है in time. So if alpha is 1, of course the second term would be 0. इसका मतलब है कि जो आपका the first term है xi would be returned as the value for the next value. So if alpha is 1, then obviously you are taking this value and moving to the next. ठीक है. So typically alpha value would be between 0 and 1. We are taking two values and take the weighted average of those and putting it as the next value. Okay. So of course, this is a parameter. You can tweak it to do modify your smoothing. Okay. So the previous value, if you want to just retain the previous value, so for example, let me explain this. If alpha is 0, so all your values would become x0, जो भी start की value है. ठीक है. So if alpha is equal to 1, then the original value वही return हो जाएंगे, x1, x2, x3, no smoothing. ठीक है. Or you can say when alpha is 0, you have such a high degree of smoothing that your starting value ही सारी होगी. Or if alpha is 1, no smoothing, original series वापस आ गई. So between the two, you can then tweak. So this is exponential smoothing that can be applied to time series. Moving on in so in preprocessing, you can also do normalizations of time series. And whenever we say now, normalization time series, so usually we are normalizing the behavioral attributes. So you can use min-max normalization as we know before. And we can also use z-score normalization. So these are the most common forms of normalization that are used for time series. So min-max, of course, if you have a time series, let's say temperature over, let's say a few months, उसका जो maximum value थी और minimum value थी, वो आपको पता होनी चाहिए. और जो आपने after normalization min-max रखना है, let's say 0 and 1, वो पता होनी चाहिए. Then you can do linear interpolation between the two. And z-score normalization, of course, is जो भी 3 months का आपका temperature data है, उसका mean निकालें, उसका standard deviation निकालें, and then transform each value by minus, subtracting the mean and dividing by the standard deviation. So why exactly is normalization required? So if you have multiple time series, so maybe you have pressure, and let's say you have temperature. So pressure has its own unit. Let's say its units are in, for example, millimeter mercury. So its value, atmospheric pressure, let's say, would typically be around 20s and 30s में होगी millimeter mercury. While temperature, again, if degrees Celsius में लेंगे, तो it will range between 0 and let's say 40 or 50. And of course, if you have some other measurement and some other units, the range might be totally different. So you cannot compare two time series effectively if you don't normalize them. So that's why we would like to normalize time series. Of course, this is application dependent. For some applications, maybe normalization may not be recommended. But if you're comparing, let's say we want to compare shapes of two time series, then normalization is recommended. Because if you normalize, then the shapes would then overlap with one another. Okay. So normalization. All right. So then again, under preprocessing, let's so if we talk about reduction, for example, so data reduction, this is a part that we talked about in data preprocessing in general. So for time series data reduction can also be thought of as data compression because many of the techniques that are used for compressing or reducing time series data are also used for data compression. So I will just mention some techniques here. I won't go into the math of them. So you can use standard signal processing techniques for time series data reduction. So we have, for example, a discrete wavelet transform. So discrete wavelet transform basically expresses a time series as a linear combination of smaller waveforms, which we call wavelets. And so it represents them as a weighted combination of smaller waveforms. And in this representation, uh, because of the localized nature of the waveforms, you are able to uh, represent the data in a more compact way. So usually what happens is, जब आप उसको expand करते हैं, so you have some coefficients. So if you don't have, if you don't want to do any compression, then the number of coefficients would be equal to the number of observations in a time series. So let's say if you have a time series of length n, okay, so you will have time series of length n. So you will have n coefficients if you do not do any compression, meaning that you are retaining each value. Or even if you retain the coefficients in the DWT space, there will be n coefficients. But usually in the transform space, you don't need to retain all those n coefficients. You can drop some coefficients that contain less information, retain only a few of them. So maybe you can only retain a fraction of these n coefficients to represent your data. So let's say आपकी time series 100 की थी, so you only use the top 25 coefficients to represent these 100 points. And then you can do all the future processing on these coefficients without worrying. And then once you are done with the analysis, you can do then the backward transformation, inverse transformation to get the real time series data after the processing. So in other words, you can do all the data mining in the DWT space. So coefficients के ऊपर ही सारी mining कर लें, and then analysis हो गया, तो then after that you can do the inverse transform to get the values in the original space. So similarly, you can have the discrete Fourier transform है आपके पास, which uses the sine and cosine functions for representing time series. So this discrete Fourier transform is more appropriate for sequences that have periodicities or frequencies that are persistent throughout the time series. So local, let's say, periodicities हैं और फिर नहीं हैं, तो उसके लिए DWT would typically give you better compression. But if you have global periodicities or frequencies, then DFT would give you better compression. और इसी तरह एक DCT भी है, which is also commonly used for image compression. So this is cosine transform, which only uses the cosine. So all of these can be used to compress time series data. The coefficients that you get after doing this transformation can be used for analysis. Once you're done with the analysis, then you can do the inverse transform. Okay, so now let's talk about similarity. So, as you know, similarity is an essential stat in data mining or characteristics in data mining. So now we want to see how we can compute similarity between two time series. So there are generally two techniques here. Of course, there could be others as well. One is, of course, using the Occlusion distance or its variant. So its variant could be, of course, the Manhattan or the Minkowski distance, but those are usually less common. We typically use the L2 norm, which is the Occlusion distance. And the other idea is called discrete time warping. It has a fancy name, but idea is quite simple. So I'm just going to discuss the idea. And even if you want to implement some of these techniques, they are usually coded in toolkits. So MATLAB में भी मिल जाएगा आपको, maybe Python की भी library मिल जाएगी, DTW की, and so on. So Occlusion distance. So usually when we are talking about similarity, we are talking about two time series की similarity. So time series, as I said, is especially if it is scalar, univariate, so you have one value recorded at each time step. So you can think of it as a graph over time. Okay. So इसी तरह एक और दो ग्राफ्स हैं आपके पास, दो ग्राफ्स की आपने सिमिलैरिटी निकालनी है, तो you can do it point wise Occlusion distance निकाल सकते हैं. So for example, so let's say कोई आपके पास टाइम सीरीज है यूं करके, तो एक और टाइम सीरीज है यूं करके, अब इन दोनों में आपने सिमिलैरिटी निकालनी है. So the idea is very simple. So take at each time point, basically दोनों टाइम, so for example let's say ये एक मेरे पास है और ये कर्व है, तो एक टाइम पॉइंट पे इसकी वैल्यू इधर की, उधर की वैल्यू ये है, द डिफरेंस, और ये सारी टाइम पॉइंट्स के लिए आपने सम अप कर दिए. सो इफ दे आर टू लाइंस, लेट्स से एक ये लाइन है और दूसरी लाइन भी एग्जैक्टली इसी के ऊपर है, ऑफ कोर्स इसका इंक्लूडेड डिस्टेंस 0 होगा. सो इफ आपकी वो एक ये लाइन है और दूसरी लाइन यूं है, इसका दोनों का इंक्लूडेड डिस्टेंस ज्यादा होगा, बिकॉज देयर इज अ लॉट ऑफ डिफरेंस बिटवीन द 2 पॉइंट्स फॉर ईच टाइम स्टेप. So what we are doing is, for each time step, we are taking the difference of the values and we are summing for all the time steps. And of course, the difference in values is the squared difference in values, including distance squared करके फिर under root पे लिया, of course. So by the way, this was univariate time series, it was a vector, then still no problem. हर टाइम पे एक वेक्टर होगा, दूसरे सीरीज का भी एक वेक्टर होगा, तो वेक्टर का आप निकाल सकते हैं, just like we did for regular data sets. But now this would be summed over all the time points. ठीक है. So just to give very simple example, let's say एक time series है 2, 3, 5 है, और दूसरी है let's say 1, 5 और let's say 6 है. So time wise you compare. So basically you have SQRT, ठीक है. So 2 minus 1 whole square plus 3 minus दूसरा क्या था, 5 square plus, तो तीसरा था so 5 minus 6 whole square. So this would be the equilibrium. So you can even think of these two as vectors, or simply इनका vector का distance निकाल रहे हैं. So you can think of these are multi-dimensional points in time space, and then you simply finding the equilibrium distance between those multi-dimensional points. ठीक है. So this would only work if you have the two time series are of the same length. Two series are of same length. Because if they were of different length, of course, then the vector operation could not be performed. Okay? So this is where the DTW approach comes in. If the two sequences are of different length, then we can apply the DTW approach, discrete time warping. So in this case, as the name suggests, we actually warp the time scale. मतलब जो time scale है, उसको हम एक्सपैंड या कोलैप्स या इवन रिमूव कई जगह पे कर देते हैं, एंड देन जहां मैचेस हो रहे हैं फिर वहां हम फिर इक्लूजन डिस्टेंस या वट एवर अदर मेजर दैट वी आर यूजिंग लेके हम उसका सिमिलैरिटी निकाल देते हैं. सो दिस इज डन इन एन ऑटोमेटिक वे. बाय द वे डिस्ट्रिक्ट टाइम वार्पिंग करने के लिए यू हैव टू डू इन ए वे सम काइंड ऑफ अलाइनमेंट करनी पड़ेगी. ठीक है, सो यू हैव टू सॉल्व ए अलाइनमेंट प्रॉब्लम. So alignment problem, as you know or you may know, it's an optimization problem. तो कोई dynamic programming या उस तरह की approach लगानी पड़ेगी. So discrete time warping में भी या dynamic time, actually it's called dynamic time warping, uses dynamic programming to align the two sequences, and then for the aligned parts, it computes the similarity. So just maybe, let's see. So let's say आपके पास एक कोई टाइम सीरीज है यूं करके over a long time और एक बहुत छोटा सा यूं करके. Obviously you know that their similarity would be the same, shape same लग रही है. तो what discrete time warping would do is वो जो ऊपर वाली टाइम सीरीज है उसको कंप्रेस कर देगी नीचे वाली टाइम के साथ, और फिर जो मैच हो रहा है फिर वो निकालेगा फॉर ईच टाइम, उसकी सिमिलैरिटी निकाल देगा. ठीक है. बोथ time scales for both were different. Discrete time warping would adjust it and then compute the similarity. Dynamic time warping would adjust it and then compute the similarity. ठीक है. So dynamic time warping की जो math है, we won't go into that. So basically we align and then compute similarity using appropriate measure. So for example, Occlusion distance is fine. ठीक है. So align the two sequences and then compute the similarity. And DTW does output a dynamic, and DTW does output a similarity value at the end of the day. ठीक है. So that was a similarity in the context of time series. What else? I think we have covered most of the preprocessing steps. So data cleaning में missing values, noise, interpolation, integration का as such issue नहीं होता. Reduction, we have discussed about reduction as well. So usually we'll be applying the techniques from signal processing for reduction and normalization, and then of course similarity. Of course, sometimes time series data which is continuous may be discretized. तो discretization की techniques हैं वो भी apply की जा सकती हैं to discretize time series data. If you want to replace those continuous values with labels, maybe your algorithm requires labels for processing, so you can discretize your continuous time series data to sequences. Okay, so now let's move on to forecasting. So forecasting is one of the most popular application of time series analysis. In forecasting, the idea is that given some recorded values of a time series, we would like to predict or estimate the value of that time series at a later time. Okay. So, and you have applications in many areas. So, for example, weather forecasting is one common application. So you have the temperature recorded for the previous 5 days. You like to predict the temperature for the next day or the next 5 days. So and of course, you have application like stock or other commodity price forecasting. Okay. This can also be used in the context of medical data, for example, for some medical prognosis task. You would like to predict the possible values of some medical uh, parameter at a later time. So maybe blood pressure, for example, आप predict करना चाह रहे हैं कि 2 घंटे के बाद क्या हो जाएगा, 4 घंटे के बाद क्या हो जाएगा, and so on. Pulse rate हो सकता है, या could be something else. So in any case, you have applications in many areas. So from the business community to the scientific community to even the humanities domain, you will have applications of forecasting. So so let me start with the simple autoregressive and come with next time I'll discuss some other concepts regarding, for example, stationarity. Let me start with autoregressive models. So autoregressive models are regression models. So we have not studied regression to a great extent in this course. We did mention regression in the context of decision trees. So regression is whenever you want to predict a continuous value, so that's regression. So here we call it autoregression because we are predicting the same type at a later time. So we have a time series data. So let's say so x1, x2, some time series data x3. Okay. So the idea would be that given this time series data, I would like to predict x4. Okay. So in autoregressive models, what we would like is to this model to be of this form. So there is some x naught. So there is some parameter w naught plus w1 into x1 plus w2 into x2 plus and so on, of course, up till w3 into x3. So autoregressive models work in this way because we are predicting x4 based on what we have seen before of the same attribute. Okay. So once we have predicted x4, usually we do not use this value in the next prediction. We use the actual value because once you have predicted x4, you will be predicting x5. But जब x5 predict करने लगेंगे, x4 की actual value आपके पास आ गई होगी. So you don't use the predicted value, you actually use the actual value all the time. Of course, वो भी एक variation है, but we won't go into that detail. Real, in most cases, we use the actual value. So in this model, of course, as you can see, there are some parameters. W's are the parameters. So W0, W1, W2, W3 are parameters. We will have to find or estimate these parameters. And this leads us to a supervised learning approach where given some data, of course, time series data, we will train a regression model which minimizes the sum of squared error, for example, between the predicted value and the actual value. And based on that minimization problem, we estimate the best fit parameters. Once the parameters are estimated, we have this equation with all the values W's known. Then if you want to predict the next value, you just have to give the previous values. So actually this, I've written this in terms of x1, 2, 3, 4. In general, this expression would then become x, let's say I is equal to, so W0 plus, so you will have W1 into x I minus 1 plus W2 into x I minus 2 plus W3 into x I minus 3. So this would be the general expression for this regression model. Okay. So given the preceding three values, you can predict the next value. Once you have learned this model, which means that you have learned the W's. Just plug in the values for the previous three values, you get estimate for the next value. So this is called a simple AR model over a time span which is three previous observations. So this example would be AR, for example, 3, meaning that you are considering the three previous value to predict the next value. Of course, this 3 I've written, I've used it here. You can try other options. Maybe you can consider the previous 5 values or 10 values or 20 values to see which one will give you the best result. So autoregressive with 3 preceding values, or autoregressive in general with n preceding values. So I think I will probably stop here. So we'll start with this forecasting step next time, and we will discuss its variants. For example, the ARMA model, which uses moving averages as well. And we'll also discuss some basic concepts like the concept of stationarity, which is theoretically good, but in practice it doesn't really work. But I think you need to know a bit of the theory. So we'll discuss that as well next time. And then we'll also discuss some other applications of time series in classification and clustering, outliers, and so on. So we probably have just 2 more lectures in this course. So looks like we'll be just completing this stuff, and that would be end of this course. So we have 2 more lectures left, and we will be completing this chapter with its basic ideas in the remaining 2 lectures.